In this video, I'm going to begin talking to you about Faraday's law. It is one of the important laws we are going to depend on during the latter part of our course. Watch out for this learning outcome. By the end of the lesson, make sure you are able to state Faraday's law in words and in mathematical form. Then also apply Faraday's law to explain the operation of an AC generator and a transformer. Before we start today's business, let's recap the key points from the week 2 lessons. We've gone through how electrostatic fields or electric fields are set up by charges, whether they are moving or not. Now, magnetic fields, we came to appreciate that they are created by moving charges. So if a charge starts moving, then magnetic fields are produced. In this video and the subsequent ones that are going to come, we are going to see how changing magnetic fields leads to an electric field. So a changing magnetic field leads to the production of an electric field, and that's our main business in this video and the subsequent ones, indeed in week 3 or unit 3 of our program. Okay, so consider a coil. Indeed, let's extend the whole thing to solenoid, a number of coils, made from a single long wire. And the ends of the wire is also connected to a meter. It can be a galvanometer, which is almost the same as an ammeter or a voltmeter. Either can be used, but it should be a sensitive one, which is a galvanometer, a sensitive one, because what we are going to do is very, very small current or voltage that we are going to measure. Now, there is no magnetic field brought close to this solenoid, and the meter reads 0. It will read 0. Indeed, it can read to the left or to the right. Currently, it is reading 0 because there is no magnetic field changing around it. Even if we bring a magnet close to the solenoid and the magnet is stationary, there wouldn't be any reading on the meter. But immediately the magnet starts moving, indeed relative to the coil, then we can see a deflection on the galvanometer or the meter, whatever it is. The deflection will be to one side when it is entering, and it will deflect to the other side when it is going out. Now, this was first observed by Michael Faraday. And how do we explain this observation? Now, we see the magnet entering and going out of the solenoid. As the magnet moves, the loops of the solenoid see changing magnetic field. So you see, this magnet has magnetic field both around it, and the magnetic field both around it is not uniform. As it enters, the coils see the magnetic field as if it is changing, and from there we can calculate or we can determine the changing magnetic field. And as it sees it, it responds by generating an EMF that drives current through the meter here. Indeed, changing magnetic field can also result in changing magnetic flux. Indeed, the changing magnetic field multiplied by the area of the coils will give us a changing magnetic flux. If we multiply the magnetic flux or the changing magnetic flux by the number of coils, we get what we call magnetic flux linkage. The linkage comes in because of this n, the number of coils multiplying the flux. So changing in magnetic field or changing in the flux or the changing in the linkage leads to the production of an EMF in the coil, which can then be read by the meter. The EMF drives current, so the meter can be a voltmeter that will measure the EMF, or it can be an ammeter that will measure the current that is flowing through the coil. So in words, how do we put Faraday's law. In other words, what does Faraday's law say? The EMF induced in a circuit is equal to the negative time rate of change of the magnetic flux linkage through the area bounded by the circuit or loop. So the EMF that will be produced in the solenoid is the same as the changing magnetic flux. Indeed, we are multiplying it also by the number of coils, making it magnetic flux linkage. And the flux linkage is changing with respect to time. So if we are able to determine this, that will be equivalent to the induced EMF in the coil. That's what Faraday's law. We are going to extend it in our subsequent videos. But I think from here, you'll be able to prove this one for yourself. Do prove it yourself. It's very, very simple. Now, let's see how Faraday's law applies to an AC generator. Here we have the basic building mechanisms of an AC generator. We have magnets that is producing the magnetic field, and we have coils. Indeed, we see only one coil here, but there are so many that are wounded together, and one wire gets to this how do we call it? Yeah, this ring here with a brush that picks the current away, and there is another ring here with a brush that picks the current also away. Now what is happening? We apply, by any other means, we apply a torque to the coil here. Make sure it rotates. As it rotates, there is a flux through this wire. You see, there's flux through this wire, and that flux will be changing. Currently, the coil is lying flat, and there is no magnetic field going through the area of the ring. They are just passing on top. I mean, the magnetic field is just horizontal like this, and they are passing on top or below of the coil. They are not crossing it. So the flux through this coil is zero at the moment. Look at what happens. Assuming it now turns to this angle, then the flux has changed from 0 to a certain value. Then if it moves further, the area that is facing or that is cutting across the magnetic field will be changing. And if the area is changing, then indeed the magnetic flux linkage is changing. Here we are, the area. If the area through which the magnetic field passes is changing, then the magnetic field linkage is changing as well. That will induce an EMF. That's what Faraday's law is telling us. Let's see how that one also, the same law applies to the use of a transformer. This is the basic building block of a transformer. We have a wire that is wounded to one side of a soft iron core. So we have this wire that is wounded to one side of a soft iron core. Let's call this side primary coil. That's where we supply our power. Then there is another side where another wire is wounded around the same soft iron core. By this side, we are calling it the secondary side because this one leads to the load. Now, what is happening? We supply a changing electric current through this wire. Take note of this. We supply a changing electric current through this one. And remember from a previous lesson, if a current flows through a wire, it creates a magnetic field around it. So there will be a magnetic field that will be directed through the soft iron core, and the magnetic field will be a closed loop. So if the current is changing, then it will cause the magnetic field through this one to also change. If the magnetic field is changing through this one, then it will induce a corresponding EMF through this wire that will drive current through any load that will be connected here. So it's the same principle. We have changing electric current, that is called inducing, or that a changing electric current that is creating magnetic field around this iron core. And changing magnetic field in this side or in the secondary side of the transformer will also induce EMF through this one. So it looks like power is being transferred from here to this side, but they are not directly connected. The power is converted to magnetic field, and the magnetic field energy also converts to electric energy on the other side. So these are the basic operations of transformer that can be explained using Faraday's law. This is what I was talking about. So as current flows through these ones, it creates magnetic field that also changes in the secondary side and cause electric current to also flow through it. In this case, we are having the magnetic field changing. In the case of the AC generator, we had the area which was changing, and if area changes, the linkage, magnetic flux linkage is changing. And in this case, the magnetic field rather is changing, which means the same thing, that the magnetic field is also changing, or the flux linkage is changing. And if flux linkage is changing, then we expect an induced EMF through the area bounded by through the core that is bounding the area of the flux. Okay, so this is basically what Faraday's law implies.